It's a very scary term, transcendental. It's like, oh, what are we getting in for now? It's just basically when we talk about transcendental functions, we're talking about functions that transcend ordinary algebra. And all that means is that it's got its own set of rules that aren't based on our strict knowledge of algebraic properties. Right? So the idea that we would just, like take the square root of both sides of an equation or subtract from both sides. There are separate rules that apply to the types of functions that we're going to look into from here on out. We're talking about trigonometric functions, we're talking about logarithmic functions, and exponential functions. And then we'll get into other types of equations that aren't functions at all. Those are called conic sections, but that's later. That's more of a third unit topic. Okay, so everything that you see in this first box here, where I say properties of exponents, that's all old stuff. Right. So definitely, at this point, you should already have proficiency in that. I mean, it's the kind of thing where it's not like, I wouldn't even say it's a prerequisite for this class. It's more of a prerequisite for the previous class. Right? So it's like you don't even get into the class that comes before this one without knowing these ones. All right. So we'll talk about it a little bit as we go, just to kind of reinforce some of them. But we're going to focus on the concept of a logarithm more than anything else. All right. So I put in a definition. I've seen definitions in textbooks that I don't really like. I'm not overly keen on them because I think they kind of sell the concept short. They sort of expect you to read their mind when they're explaining it. I saw a definition in a textbook that says a logarithm is an exponent. And it's like, well, I know that sometimes we call different things by the same name, and then sometimes we call the same thing by different names. It's just the nature of the English language, I guess. We try to be as complicated as possible. But my first thought was like, well, if a logarithm is an exponent, then why the hell don't we just call it an exponent? Why do we have to have this term called a logarithm? A logarithm is actually not just an exponent. In a sense, I guess you could say it is, but the result of a logarithm is an exponent. The arithm part of logarithm it's the same root as algorithm. It's a set of processes. Right? So when you're finding a logarithm, you're determining using a series of steps the result of that process, giving an exponent as an answer. All right. So it in and of itself is not an exponent. It results in an exponent. Right. So I can say here, I'm going to read my own definition for you. Logarithm is the method by which we determine the power of the power a number must be raised to in order to equal another number. Right. But so in effect, it is finding an exponent, but there's so much more to it than that. Right. So when I say something like, here's an exponential equation, 5 to the x is equal to 2, I'm really asking you to determine what power 5 has to be raised to in order to give a result of 2. Right? And so there's a bunch of different ways to do it. One way is trial and error. Another way involves a logarithm. There's also graphical approaches. But let's say we're doing it with trial and error. If I want to raise 5 to a number and get a result of 2, I could say, all right, I think it's 5 to the first power. All right, that didn't work. Well, it's got to be less than 1, because if I go higher than 1, 5 to the second, for example, is going to get me further away from my goal. So maybe like 5 to the 0.5. All right, closer, 2.236 and so on. Maybe 5 to the 0.4. And not big enough. Maybe 5 to the 0.45. Too big. 4. Not too big. Too little. Too big. Too big. Still too big. I'm just guessing and checking here. All right. So maybe it's, let's see, I did this one. 1 got me too far, so maybe it's like 0, 5. Yeah, I'm getting pretty close. Maybe you're satisfied if you 0.4305, that gets you pretty close to 2. You can look at that and say, oh, well, that's close enough. I'll just call that my answer. All right, but I'm kind of a perfectionist when it comes to this. Let's say we go to 5, 5, and not big enough. 5, 9, 6, 7. Oh, too big, but not by a whole heck of a lot. So maybe 6, 9, 8, 7, too small. 7, 5, 7, 9. Oh, almost there. 7. Ooh, so close. Maybe throw a 5 at the end. So 6, 6. Oh, too big. 6, 5, 5. 6. Oh, so close. Too big though. Maybe a 5. Maybe a 5, 5.
Professor, this is horrible.
This is so great. I'm having so much fun. I would love to do this for
this is
every
horrible.
problem. Can you imagine doing this for every single problem that involves
I don't
you
think
having to
I'd
solve for a
make
variable
it.
exponent? It would be so wonderful. I think you would enjoy it. I mean, it's an acquired taste. It's like coffee. You only think you don't like it until you become addicted to it. So
I like coffee.
it just takes it's an
Oh my
acquired
God,
taste.
you're so close. Jeez.
Oh, like almost there. Oh, I'm gonna get it now. 1. Nope. 2. Oh, there we go. Oh, I did it.
Oh my God.
I guessed and checked my way to perfection. All right. Now, that being said, I could also have solved this equation a couple of different ways, because whenever you want to solve an equation, you can take the left side and write that as its own equation. Take the right side and write that as its own equation and find where they intersect. So I can do something like y equals 5 raised to the x power. Y equals 2. And I just see where they cross right there. It'll give me a rounded answer, but that's what you would get if I took my exponent here and rounded it. All right, so that's another way you can do it. All right, but another way you can do it is by finding a logarithm. All right, so when I say find the exponent that 5 would have to be raised to in order to equal 2, I'm actually saying find the log base 5 of 2. Now that's actually, I mean, I can't emphasize enough just how stupid that sounds and how inconsistent with what we're actually looking for it sounds, because when I tell you the definition, I'm saying, okay, when I have log base 5 of 2, it means what does 5 have to be raised to as a power in order to equal a result of 2? There's really not much about this expression that makes you think that. All right. So I'm saying, what does this have to be raised to? This number have to be raised to equal this? What does 5 have to be raised to in order to equal 2? That's what this expression is asking us. It doesn't very much look like that, right? But that's really what it is, right? So we go into Desmos, we look around in our different functions, we see miscellaneous, and you see one that says log. So again, Desmos, regular commands. You look at you're in the little field there where you type your equations and expressions. Tap functions. You go to miscellaneous, and then you'll see log and then log A. If you select log A, you see the notation of log A. It's got a little base there. It allows you to put whatever base you want. All right. So I can tap in here a 5, and then a 2, and it'll, I mean, no guess and check required. Let's go back here. That decimal that it took me a couple minutes to find pretty much gave us that. The only thing, it put a 3 at the end. I put a 2. I don't know. Now I'm questioning. Yeah, 3 would have worked also. All right. So the question of rounding, I suppose.
Is it possible for you to just go over again how you got to the log? It was miscellaneous.
So functions, miscellaneous, grab the one that says log with a little base of A, a little subscript of A.
Okay.
Now, if you're ever in doubt when it comes to Desmos, you just start typing a function in, and it'll start writing it as in italics. But once it recognizes it as a legitimate function, it'll correct it to ordinary font. That's how you know Desmos is recognizing it. You see this this little key here, that little A with the little subscript of B. That's a base. It's right next to the 1, 2, 3.
Yeah.
So you pop that in there, type in the 5, and then you can essentially do it manually. All right. So if you're ever in doubt, you just start typing away. Odds are you're gonna find it. Right? Because Desmos recognizes a lot of different functions.
Thank you.
Right? No problem. So we want to get to a point where we're comfortable converting back and forth between exponential functions and logarithms. Right. So what I like to do is look at a log in general terms. I'll use capitals. All right. So the lowercase b stands for base. I don't know if I said lowercase b. I meant base b. It's uppercase b. You know, b for base. E for exponent. And n for number. All right. So what this is saying is that b has to be raised to some number power to give you the e result. All right. I'm sorry, I got them backwards. Apologies. It's b n e. My son's name is Ben, so I have this habit. I can't not take the 3 letters B, E, and N and not write the word Ben. So anyway, so what we do in a circular pattern is we work our way around and we create an exponential out of this. So we start off with a base B, raise it to the E power, and that result is equal to N. N is some number. All right. So these two forms are interchangeable. So as long as you have this relationship, you can always go back and forth and you can convert from exponential to log form and vice versa. All right. So for example, I'll just kind of shrink this up. I'll just do the example below it. Because it's natural to wonder, how did we get from the 5 to the x equals 2 to the log base 5 of 2 equals x? All right, so if I tell you that I have some expression 5 to the x and that expression is equal to 2, the 5 is occupying the position of the b. The x is occupying the position of the e, and the 2 is occupying the position of the n. So in log form, we could write this as log base 5 of 2 is equal to x. And since ultimately what we're trying to do is solve for x, you look at the two forms of the equation, they're both equivalent, but one has x alone. Ultimately, when you solve an equation, you want to get x alone. So that would get the job done. Right? Some people don't like that method. There's a slightly different approach that some folks will use. It's really just a matter of just finding the mnemonic device that works for you. There's plenty of options online, but the one that I find that people kind of gravitate towards the most, aside from this approach, is the idea that the base of the exponential and the base of the logarithm are always going to be the same. If you write it in the appropriate form, you notice how we have the x on the, in exponential form, you have x on the left and the 2 on the right. In log form, the positions switch. So the 2's on the left and the x is on the right. I don't particularly care for that one because it relies so heavily on everything being in the same form all the time. But yeah, you just find the way that you like the most and go from there. Right. Now, when it comes to, I'm just thinking it's probably about the time for the word of the day, which would be simple. Simple is the word of the day. Right, so simple is the word. So when it comes to situations that involve variables, like the subject of the log, like the thing that's contained within the log is variable in nature, it's not always going to be a simple matter of just typing it into the calculator, whatever calculator you're using. These problems, you just type away. You know, you just type these numbers in, you use log base function, the log base A, you know, if I'm doing number 5 at the bottom, put in a 3 here, put in a 42 and happy days, you know, oh, 42, I said. Now happy days. You know, that stuff's easy. But when you have instances where you got to solve equations and simplify, we have to use some properties of logs. One of which is the product rule. We also have the quotient rule, the power rule, and then the change of base formula. Change of base we'll worry about down the line, but for now, the product, quotient, and power rules are really important. All right, so a product rule tells us that if you have a log with some base, doesn't matter what the base is, and that log contains the product of two factors, right? So m times n. What we do is we break it up into two separate logarithms. So we have the m, we would take the log of the m and separately add to it the log of the n, all right, maintaining that base throughout. So that's what we call the product rule for logs. There's also a quotient rule for logs, but if you understand the product rule for logs, you can kind of figure out the quotient rule pretty easily because it's really not too different conceptually and even structurally. You have a quotient, as in you're dividing two factors. I mean, factors, for lack of a better word, is really two, you know, a dividend and a divisor, but you have two parts to the fraction separated by division. So that division corresponds to subtraction. Right? So I would take the log of the top of the fraction and subtract from it the log of the bottom of the fraction. The power rule is the fun one because all that tells us is that if you have a power contained within a logarithm, that power shifts over and becomes a coefficient. And that's what I meant by this is a transcendental function, because these aren't rules that you can apply in algebra. Like, can you imagine just making the power into a coefficient? Like I said, let's say, for example, I have x squared, and I was like, yeah, you know, for the hell of it, I'm just going to call that 2x. Why? Because I want to. Because I'm just going to take this and just move it out in front. That's not a thing, right? So, I mean, there is something in calculus that you'll do that's kind of similar to that, but there's a very good reason why you're allowed to do it there. But it's not just because I want to. You know, here with logarithms, it's still not just because you want to, but it's a little bit closer to that because it's a rule that we just believe is true. Later on, you get to the justification for why it's true. All right, so let me show you what it looks like in action, because we have these multi-step problems, but they all just basically boil down to us simplifying some logs. And it's not overly complicated. So I have a product here, x to the 5th times y. So I'd apply the product rule for logs. I'm just going to write product rule. Right, and again, it's product rule because I got a little product there. It doesn't, you know, the little dot wasn't there. I threw it in, but it's still there. Right. So I'd write log base b, always have the base there, of x to the 5th plus log base b of y. All right. When you expand logarithms, we're writing them in simpler forms. And what I mean by a simpler form is that you want to have less stuff contained within the logarithm, right? So instead of having log of x to the 5th y, I want to have just log of x. I want to have just log of y. I can have a bunch of different logs. I don't want to have log of monstrosity. I want to have multiple logs with very simple stuff in it, right? With that in mind, we always handle product and quotients before we handle powers. All right. And that's because if I were to try to make this coefficient, this 5 into a coefficient of the log, it wouldn't make sense because that y doesn't have a power of 5. It wouldn't apply. All right. So then I would look at this 5 here now in this step because I've isolated the term that has that power of 5, so power rule. That power becomes a coefficient. So I'd be looking at 5 log base b of x plus log base b of y. All right, and so once there's only a single solitary argument, we call it an argument contained within the log function, then you're done. Right now, there could be multiple log functions, and that's fine. You're not really concerned about that. You're concerned about the quality of what is contained within the log function and how complicated that is. Right? It's just an x here. It's just a y. Mission accomplished. Right? So this next one has a quotient. So I'd apply the quotient rule. So I break up the log by the quotient. So I'd have log base b of s to the 4/5 power minus log base b of u to the 7th. Right? One part of the fraction gets its own log, the other part of the fraction gets its own log. Then I would apply my power rule again. This time I'm going to do it in 2 separate instances. All right, so those exponents hop over to log, and we end up with 4/5 log base b of s minus 7 log base b of u. These skills are just, I mean, they're really formative skills. They're just trying, or designed more than anything else, to get us geared up to be able to handle more complicated log situations, right? But a log function itself, we'll get into the graphs as we go, but if I were to graph y equals log of x, whatever it happens to be, I could just write a good old fashioned log, log, open paren, type in an x. You're looking at a function that's increasing in nature and then levels off. Applications of that are all over the place. Anything that models growth, physical growth. I think I gave the example of, the heights of a human over a short period of time. Like an infant growing up, getting older and older and older. Dramatic rate of growth initially, but then the rate of growth slows down as the individual gets older and older. Otherwise, I mean, if we were a linear relationship, that individual would be like 700 feet tall by the time they were 40. Right? So the rate of growth decreases. Yeah, and probably more of a piecewise function in that there's little jumps in height over time, the growth spurt, but that's essentially a nice, easy, relevant application of a logarithm. But what we need to be able to do is be flexible enough to be able to handle the logarithms that are very complicated initially, and by handle them, I mean represent them in a more simple form or a simpler form, and make it nice and easy to work with. All right. So C and D, geez, I see the letter C there, so I just went after it like an animal. Numbers 3 and 4 is what I meant to say, are applications or extensions of this. But you can see number 4 is pretty crunchy looking, so I'm going to put a star on that one and let you try that one on your own. But we'll do number 3 together because this is an interesting one. There's a couple of different ways that you could represent it, and I'll do it both ways just so you get a sense of what's going on here. But one way to look at it, if you're more, I guess, rules oriented, you look at it, you see quotient. All right, what did he say when we see quotient? Quotient means quotient rule. Okay, log base b of 1 minus log base b of c to the 8. All right. Then what did he say? He said, okay, I see an exponent. I apply the power rule. I don't do much with trick questions, but I can tell you right now, this is the only kind of trick question that I ever throw at anybody in this kind of course. Because the log base b of 1, we could actually do something with that. Right? But I'm going to rewrite it anyway. Log base b of 1 minus 8 log base b of c. So you look at this and you think, mission accomplished. We did it. Moving on. But let me show you another way to do it. And in showing you the other way to do it, you'll see that we could actually go further with this one. All right. So I'm going to take the same problem right from beginning. Let's see. Close enough. Right from the beginning. When it gets late in the evening, I start speaking in sentence fragments. It gets pretty weird. All right, so log base b of 1 over c to the 8th. Now, 1 over c to the 8th, just because logs transcend algebra doesn't mean that you don't have to do algebra or you're not allowed to do algebra. You can still do algebra. All right, transcending algebra means that you're not limited to algebra. All right, so 1 over c to the 8th is the same as saying c to the negative 8th power. All right, so I could write this as log base b of c to the negative 8th. All right, one of the properties of exponents tells you that you can move a term from one part of a fraction to another as long as you negate the exponent. Right? So I'm choosing to move this up to the top, and in doing so, I negate the exponent. If you're unsure if what you're doing is legit, put it into Desmos. All right? So 1 over, you could even use the letter c. C raised to the 8th. It'll ask you for a slider, but that's fine. It'll give you some numbers. That's great. And then try c raised to the -8. And just make sure that it's always going to give you the same decimal. All right. So no matter where I slide my slider, those decimals are always the same. So these two, or at least there's reason to assume that these two expressions are equivalent in value. So if you're ever unsure about a rule, you could use Desmos to verify it for you, which is a nice feature. Now, with that being said, I'm looking at this and I'm seeing some power rule. Right? Exponent jumps over the log. So this becomes -8 log base b of c. All right. So somehow this log ended up being equivalent to -8 log base b of c. Now you'd look at it and say, well, when we did it the other way, we got this log base b of 1. All right. Well, let's take a look at that log base b of 1 separately really quickly. It's kind of off on the side. So I'm just going to, maybe I'll do it at the top. Log base b of 1. All right. We're going to try to figure out what that is. I'm going to set that equal to some value. I don't know what the value is. I'm just going to call it x. All right. If I want to convert this over into exponential form, remember this is my capital B. This is my N, for quality N. And this is my E. And we want to get it into B raised to the E equals N form. So when I rewrite it, it would be B to the X is equal to 1. And at first glance, it doesn't seem to be overly helpful. But when you think about it, you're asking yourself, what would I have to raise some number B to in order to get a result of 1? Well, any number to the 0th power is equal to 1. All right, so if I take some number B and raise it to the 0th power, I can put my slider wherever I want. That B to the 0th is always equal to 1. Okay, so that result is always going to be equal to 1. So log base B of 1 is equal to 0. And so therefore, this cancels to 0. And our final result would actually be -8 log base B of C. All right. So there's that extra little twist in there. But that being said, let's say you're taking a test and you're panicking. It's not atypical. You're going to panic in a math class. It's probably going to be during a test. You're not sure. You see the log base B of 1. You're like, I don't know what to do with that. Type it in. Log. Put in a little b there. It'll ask you if you want a slider. Sure, I'll put a slider there. It's saying that for negative values, it's undefined, but everywhere else, it's equal to 0, right? Now, what that means is when I look at a log function, y equals log of x, I'll just do ordinary log, common log. A log function doesn't exist beyond the y-axis. It doesn't even exist at the x-axis. So we're not even looking at negative values to begin with when it comes to x. You can't take the log of 0. You can't take the log of a negative number. All right. So can't take the log of 0. So you can't take the log of 0 and you can't take the log of a negative number. Those are ironclad relationships. All right. It's undefined when that happens. The log function just doesn't exist. All right. So looking at only positive values for B, So I would have to start somewhere, so I'll start at 0. You see that no matter where I put my slider, I could even extend it beyond the 10. I'll put it like to 1,000. No matter where I put the slider, for any positive rational number, or not even rational number, or real number is what I meant to say, the log value of 1 for a real base value that is positive, the log of 1 is always going to be equal to 0, right? So if you see, long story short, I know it took a while to get there, but if you see log of 1, regardless of what the base is, it's always going to go to 0, right? So until you get into more complicated math, that's going to be the way of it, right? So I'm going to star some problems for you to try on your own. All right, so everything in this section here, I'll put stars on each individual problem. There are some all these problems down below are doable at this point. Some of them are more challenging than others, but I'm going to put stars on everything, and we'll start off class next time going over these. Okay, because in theory, this is stuff that was covered in the previous course, but theory and practice aren't always the same thing, / hardly ever are the same thing. Right. Some of the other ones on the next page, they involve natural logs and stuff like that. So I'm just going to stop starring. I don't want to go too crazy. So I'm basically saying try all the remaining problems on page 35. We'll talk about page 36 and 37 because there's some word problems there that are a little on the crunchy side. Some of them are pretty easy, but some of them are a little bit spicy. So I don't want you to stress out too much over those. Especially since some of them are getting into like compound interest, and we haven't talked about that, right? So, but that's where we're going. Some nice applications of logarithms, but before we do that, we need to really get a good grasp on this stuff. All right, so I'm going to stop the recording.